Hi, good evening, everyone. Just wanted to do a little bit of test prep here. So this is just going to be kind of a broad strokes, general review, and then I got some specific requests, so I'm going to run through some examples of those, and I'm going to just try and highlight some things. Calc 2 is a class that requires a pretty hefty amount of memorization. So I understand that sometimes we have to prioritize what we memorize, because sometimes there's just not room for it all. So with that being said, let's go ahead and get started. So let's see what we can recall about. Sorry, it's picking up my hand there. Inverse functions and the inverse function theorem. Okay. So we want to know when a function has an inverse. Some functions don't have inverses anywhere. Sometimes we can truncate a function to have an inverse, right? So suppose we take the parabola f of x equals x squared. Using our handy dandy tool for testing whether or not an inverse function exists, the horizontal line test, or HLT, we see that in general, this function doesn't have an inverse. But if we restrict the domain, if we say f of x equals x squared on the interval 0 to infinity, then we have something that looks more like this, and that indeed passes our horizontal line test. Okay, so what if our function is very difficult to graph, right? What if it's something that we don't know? It's not an easy function to figure out, and our graphing utilities find it computationally expensive to plot, right? So there's a few things we can do. We need to guarantee, or we want to show. So we want to show that either f prime is strictly positive or f prime is strictly negative on a domain, or if we assume that there are two places where the y values are equal, so f of x1 equals f of x2, those places actually coincide. So there's no separation. So graphically, that's just going to say, like, if it doesn't pass the horizontal line test, then these two values can be distinct. So this would be our x1 and x2. But if it does pass the horizontal line test, we always have that x1 equals x2, and that follows logically. Generally, the algebraic method, this method is a little more difficult to work with. It's nice to just work with derivatives if we can. That's kind of an easy way to test that. And graphically, what's going on there is, well, if something's always increasing, then as we scan left to right, this point will always be lower than this point, which will always be lower than this point, if it's strictly increasing. Now, if it's ever equal to 0, we can have constant functions, right? So we just have like y is 3, for example. And that's a problem, because that definitely doesn't pass the horizontal line test. So it has to be strict inequality there. Okay. I just wanted to go through the statement of the inverse function theorem again. So we have to make sure that, well, I'll write it first. So we have that f inverse prime of y naught is 1 over f prime of f inverse of y naught. Okay, and the point y naught, x naught is on the graph of f inverse, right? So really, the only way we're going to get in trouble here is we have to make sure that our f function is differentiable at whatever we put in the argument, and we also have to make sure that f prime is non-zero at f inverse of y naught, right? So it looks like an x of y naught. So as long as we satisfy those conditions, we can apply inverse function theorem, and it is in general much, much, much easier to use than trying to invert a function, prove that an inverse exists, invert it, and then take the derivative anyway. So in general, it makes our life a lot easier. All right. Next thing. So I just wanted to quickly recall that the derivative of e to the x is in fact itself. That's what makes it kind of special. And we have that the derivative of log of x is 1 over x. Now these, we just have to memorize these. This one, not so bad. This one, a little bit harder. But the important thing to keep in mind here is that chain rule is always active. It's always happening, right? So let's take, for example, if we have d dx of e to the 3x, right? The way this works with the chain rule is we're going to say, okay, well, we leave it alone and then multiply by the argument. Okay, and so that ends up being 3e raised to the 3x. Okay. In generality, we have that the derivative of e to a function of x is e to that same function of x times the derivative of that function of x. Okay. And similarly for the log function, if we wanted to differentiate log of g of x, say, need one more, that would be 1 over g of x times d dx of g of x, or we can just denote this g prime, so it's g prime of x over g of x in generality. Okay, now I want you to be very, very meticulous about your notation, and that's really going to be important when we start working on L'Hopital's, but I'll get to that in a little bit. Okay, so just some helpful log properties. You don't have to memorize these. Highly, 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 highly recommend it. There's quite a few times where it's just going to make your life so much easier. If we have x over y, this is log of x minus log of y. And honestly, I think the most important one is, let's say we have like log of x to the 3/2 power, right? We can actually slide that power down in front and we have 3/2 log of x. And I think I know which one of those I'd rather differentiate. It's also important to remember that the natural log and base e exponential are inverses of each other. So e to the ln of x is ln of e to the x, which are both x. And just as a recap, we want to remember that the integral of dx over x is the natural log of absolute value of x. And that's super important. You have to remember the absolute value. Now, there are times when we can drop the absolute value. It's not necessary, for example. So if for some reason we have like log of absolute value of x squared, right? You know, provided a domain where this is non-zero, but we know that something squared is always going to be positive, except for 0. So we could, in fact, on an appropriate domain, so let's say x greater than 0, we could, in fact, drop those absolute values. But you have to justify why you're dropping those absolute values. Okay? And since e is its own derivative, it's its own integral as well. Now that can be a little more complicated, but in its base form, this is just e to the x plus c, right? Okay. Let's go ahead and move on to L'Hopital. Now, I have a bit of a pet peeve when it comes to L'Hopital's rule. So let's suppose we're working with a rational function, a ratio of polynomials, and we have limit as x approaches infinity of something like 3x squared plus 4x plus 6 over 2x squared plus 2. And what can sometimes happen, particularly in a Calc 2 class, is students get L'Hopital's rule and they just kind of use it on everything that they possibly can. So this, I could very well see this being kind of a trick question because there's an easy way to do it, but if you insist on using L'Hopital's, it can it can introduce more room for error. It can take a lot of time, right? So we could say that, okay, well, this is indeterminate, and I like to justify why I'm using L'Hopital's, right? So this is indeterminate of the form, and since x is approaching infinity, this is an indeterminate of the form infinity over infinity. So we apply L'Hopital, and we get that this is equal to the limit as x approaches infinity of the derivative of the numerator, which is 6x plus 4, over the derivative of the denominator, which is 4x plus 0. Okay? But if we try and plug infinity in, so to speak, we run into the same problem. We're still indeterminate of the form infinity over infinity, so we say, okay, well, now we apply L'Hopital's again, right? And we have limit as x approaches infinity, and we differentiate the numerator again. We have 6 over 4, which simplifies to 3 over 2. But all of this was unnecessary because if you recall from calculus, or pre-calculus, when we have a ratio of polynomials like this and the degrees are even, in this instance 2, we can just take the ratio of the leading coefficients and have 3 halves and we're done, right? The same story with if we have something like 3x plus 1 over 2x squared plus 4, the bottom term is going to dominate in the ratios, so this is just 0, and we don't need L'Hopital's to figure that out. So just use L'Hopital's when you need it, but there are times when you don't actually need it. So just keep that in mind. And recall that we can't just go applying to L'Hopital's to any limit that isn't working out for us nicely. We have to justify things. So we want it to be either infinity over infinity or 0 over 0, right? Sometimes we'll end up with stuff like 0 times infinity, or let's say 0 to the infinitieth power, right? We have to do some algebraic magic to make it work and look like one of these. Sometimes that's multiplying by the conjugate, multiplying, I think a quick example might be something like x ln of x, right? We could equally write this as ln of x over 1 over x. And we could do some manipulations with that. Just off the top of my head, I don't think that's going to work. But sometimes we have to do just these little tricky things. So keep an eye out for those. Okay, next thing, hyperbolic functions. Okay, so hyperbolic functions are just a little pit stop on the way through this class. They're, in my opinion, not the most important thing that we'll cover, but we still have to cover it. And things you have to know is you have to know the form of sinh, which is e to the x minus e to the minus x over 2. You have to know cosh. You have to know cosh of x, which is e to the x plus e to the minus x over 2, and you have to know tanh. Which we're in luck because it mirrors what we know from just, our familiar old trig functions. So this is not negotiable. We have to know these off the top of our head. Now, as far as like hyperbolic secant and the derivatives thereof, I'm a little less concerned with that. These are really your primary suspects. These are things you're going to see the most of. So again, in order of, or if we're trying to prioritize what we have to memorize and what we don't, what we have to be most familiar with, I would absolutely prioritize working with these three, your primary culprits. Okay. Now we get to a little more sophisticated integration techniques, right? We know U sub, we know how to integrate basic functions, sine, cosine, all that jazz. Now we have a little bit more nuance going on. This is a very powerful tool, and it's one of those things where you don't have to memorize the formula. You can derive it, but trust me, life is a lot easier if you have this burned into your memory. Next thing is trig integrals. So this is subtly different than trigonometric substitution. That's its own thing. Trig integrals are just integrals that involve trig functions. So we already know how to do some of those, primarily using U substitution. But the biggest thing with trig integrals is your Pythagorean identities, which is sine squared of x plus cosine squared of x equals 1. This is a memorize. We have to know this one. Now, the lucky thing, though, is that if you know this one, you know the other two, right? There's actually 3. If we divide everything by sine squared, we get 1 plus cotangent squared of x is 1 over sine squared is cosecant squared of x. If we divide everything by cosine, we get tan squared of x plus 1 is secant squared of x. So know this one, and you know how to get to these two. So you don't actually have to memorize them if you feel comfortable deriving those formulas. But most of the time, these trigonometric integrals, they just boil down to make some sort of substitution. So we either use a power reduction. So we'll recall that power reduction is cosine squared is 1 plus cosine 2x over 2, and sine squared is 1 minus cosine 2x over 2, if I recall correctly. Yeah, we'll use basically one of these identities, possibly both, and then we'll kind of finish up the integral with a nice U substitution. That's generally how those play out. Again, sometimes you have to do a little bit of finicky algebra kind of stuff, but like I said, I just want to go through kind of a broad strokes. Okay. Something you should also have at least an idea of is generally what the hyperbolic functions look like. So this kind of helps you understand. I totally missed the origin there. This kind of helps you understand just, how the limits are working out. It's just good to have the picture of these functions in your brain. And they're very similar to things that you already know. Like this one kind of looks like x squared. This one kind of looks like our inverse tangent with these horizontal asymptotes. And this one kind of looks like x cubed, but very gentle. So it's not a huge stretch to go ahead and just kind of memorize the general shape of these things. And like I said, it can really help you out with the limits. Okay. So I got a request to kind of run through some. Well, it was both for hyperbolic functions and some proofs. And I'm not going to expect a very high level of mathematical rigor out of all of you. I understand that, you know, proofs they're a scary thing to start approaching. So keep that in mind when we ask you to show something, we ask you to prove something. Like, you know, don't freeze up. Try and work with us. Try and work through something logically. But to kind of give you a stepping stone into that, I wanted to do an example or two with you. So, example, we want to show that hyperbolic cosine is an even function. And we'll recall that an even function satisfies a property hyperbolic cosine of x is equal to hyperbolic cosine of negative x. Okay? So that would just be symmetry about the y-axis. Okay? So we can prove this identity kind of two ways. But let's go ahead and write out exactly what in terms of the exponential, what the hyperbolic cosine looks like. So these are things that you should also have memorized. Cosh of x is e to the x plus e to the minus x over 2, right? And cosh of minus x is e to the minus x plus e to the minus x over 2. So cosh of minus x minus, there we go, is e to the minus x plus e to the x over 2. Now, we'll recall that the real numbers are commutative under addition, which means that we can exchange these two. So we have that cosh of minus x is e to the x plus e to the minus x over 2. And since we worked on these things separately, we didn't assume equality from the beginning. We just manipulated each individually. We have that these two things are equal. So we have that cosh of x is equal to cosh of minus x. And since x was arbitrary, we have shown that cosh is indeed an even function. Okay, and that might be a little hard to understand right now, but proofs are a little bit more nuanced than calculating integrals. So I just want to challenge you all. So I don't think I want to go through this entire one, but I want you to think about how you would approach something like this. And it's cosh, not cosine, sorry. Cosh squared of x minus sinh squared of x is equal to 1. Okay, so prove. Okay, so I just want you to take a little moment here and think, okay, well, how would I go about proving this, right? We can't assume that this equality exists. So we can't say, okay, you know, I'm going to multiply both sides by 1/2 and, you know, do some nonsense there. We want to show that it's true, and if we do something like that, we're already assuming it's true, and that gives us a circular proof. So that's not what we really want to do. So just think about it. Really, proving identities like this boils down to you start with one side and manipulate it algebraically until you get to the other side, if you can. So try using your exponential identities and see if you can get to this. Okay. So like I said, I got a few requests for hyperbolic functions, so I just wanted to run through some quick examples. So find the derivative. We'll say g of x is sinh squared of x. Okay. So we're gonna have to use chain rule here. So g prime of x is the 2 comes down, and then we're going to multiply by the derivative of sinh of x. Okay, and you'll recall that from Calc 1. I know I may have kind of a strange way of thinking about chain rule, but really this is the composition. So we're stuffing the sinh function into x squared. So that's how our composition works. So we're going to differentiate the x squared first. The 2 comes down and gives us 2x, but then chain rule kicks in, and then we multiply by what was going inside of x. So we get this. So we have g prime of x is 2 sinh of x times the derivative of sinh of x, which is actually just cosh of x. Okay. Now the cool thing about the hyperbolic functions is that they behave pretty similarly, under derivatives. They behave pretty similarly to our regular sine and cosine trig functions, except we're a little lucky in that there's no sign switching, which is kind of interesting. So if we differentiate cosine, we get negative sine, for example. But whenever we differentiate cosh, it just goes right to sinh, and sinh goes to cosh, which is I think quite a bit easier to wrap your head around. Okay, so let's try an integral with one of these things. So let's try the integral of sinh of the square root of x over square root of x dx. Okay. So let's try u sub. So we'll say let u equals to the square root of x. Then du is 1 over 2 root x dx. And when you do calculus long enough, you'll have that one memorized. But if you don't believe me, go ahead and double check. So I want to get rid of this 2 on this side. So I'm going to say 2 du is 1 over square root of x dx. So now our integral looks something like sinh of u times 2 du, because all of this is just another way of saying 2 du. Okay? So we have 2 sinh of u du is 2 cosh of u plus c. And then now we started with x's. We want to finish with x's, right? So now we make that substitution back. We have 2 cosh of square root of x plus c, and we're done. Okay? All right, now I wanted to run through an example of L'Hopital. Okay? Now, this isn't the spiciest example of L'Hopital, but I think it's a good one to kind of go over, because it allows us to tie together our theory with our intuition, right? So let's take a look at limit as x approaches infinity of log of the square root of x over x squared. Now, if we think about this as competing functions, right? The growth rate of the log function is actually pretty low, right? Because if you think about what the log looks like, it kind of just ambles off gently, right? It does go to infinity, but it takes a while. But if we think about so this is log of x, right? If we think about what x squared looks like, it's kind of racing off to infinity. It gets larger very quickly. So if we're looking at the ratio of these two things, we imagine that it should approach 0, right? Because the denominator is going to get larger than the numerator pretty quickly. So intuition-wise, we have a feeling that this should go towards 0. So first thing to do always the first thing to do with limits is we see what happens if we just plug this in, right? If we say, okay, well, what if it does go to infinity, right? Well, we have something that is indeterminate of the form infinity over infinity. So we apply, or therefore, therefore apply L'Hopital. So we have that our limit up here is equal to, and we're going to start taking some derivatives. So the derivative of the denominator, nice and easy, just 2x. The derivative of the numerator is 1 over the square root of x times the derivative of the square root of x, which is 1 over 2 root x. I'm just doing some simplifying here. We have 1 over 2x over 2x, which ends up being limit as x goes to infinity, 1 over 4x squared, which is 0 when we finally take the limit. Now, yes, you have to show the limit at each step until we plug that in finally. And I like to put a little LH here, just so we know that on the face value of it, right, these two things are not equal. If we just write the equal sign, it's difficult to understand that that's what you're trying to do. So just indicate to us that, you know, we're doing L'Hopital's rule and these are equal, but we took a derivative in the meantime. So just watch out for that. But this answer does indeed, it verifies our suspicions that, yeah, the denominator grows much more rapidly than the numerator does. So the limit is in fact 0. Okay. Let's move on to some integration. So integration by parts. Okay, so example, let's say we have log of the square root of x dx. Now, I chose this particular example because we have this nice little formula that u dv is uv minus integral v du, right? Sometimes these, like u and v, are not actually all that complicated. Now, keep in mind what's on the other side of the equal sign here. So the strategy that I try and tell students is that when we're integrating by parts, we're going to look for a product of functions, and one of them is screaming to be differentiated, generally. Because think about it. We have log square root of x times 1, right? Technically, this is a product of two functions of x, right? It's not a particularly interesting one, but it is. So when we set this up, we want to select a u that differentiates well, so to speak. So if we say, okay, well, u is 1 and our dv is ln of the square root of x dx, right? If we try this, well, we're kind of in the same boat. We don't know how to integrate this dv, right? Because eventually we want to find v, so we're going to have to integrate this dv. But if we turn this on its head and we say, okay, let's scrap that. Let's scrap that. Okay, let's say, what if u is ln of square root of x, right? Well, we have that du is 1 over root x times 1 over 2 root x, right? And dx. So du is 1 over 2x dx. Okay. Now, and let's, we need the other part of it. So we need dv, right? But that just ends up being 1 dx because that's kind of what's hiding out here. So that tells us that v is just x, right? So let's roll with this. Let's see where this goes. So we can do this. We can proceed this way, but I'm actually going to encourage, I'm going to encourage just a little bit of algebra in the front half, okay? So let's try this. Most of this is going to stay the same, but a little bit of algebra is actually going to save us a lot of messing around with a coefficient. So I just want to emphasize that what's that expression? A penny's worth of algebra is worth $1 of calculus if we use it correctly, right? So let's take a look at this. Can we reduce this to a simpler problem? Well, if we express this as x to the 1/2 dx, we can use the properties of log to actually pull that power out and in front of the integral. So that we can just do log of x dx, right? And that's actually looking considerably easier, right? So I'm going to put this little 1/2 in its own box for half a second, and we're going to integrate this by parts, okay? So as I was saying, let's say u is ln of x and dv is 1 dx. That tells us that du is 1 over x dx, and our v is x, right? We're kind of building, you know, we need little pieces, you know, just, okay, what's this piece, what's this piece? It's kind of like a recipe, you know, we need this piece and we need this piece. Okay, we put it all together, boom, we have our integral, right? Because now we have this piece and we have another integral to solve, okay? So I claim that, okay, ln of x dx is u times v, which is x ln of x, minus integral v du so that's x times 1 over x dx, right? Well, observe the cancellation here, right? So what this really boils down to is x ln of x minus integral of 1 dx, which is x ln of x minus x, and then we have our arbitrary constant, right? Okay. Now we're very close. The reason I put this off to the side here is I didn't want to mess with the coefficient until later. So we have this, but we really wanted to have an extra coefficient of 1/2, so we can just multiply both sides by 1/2. So we have 1/2 integral ln of x dx is 1/2, and I'm going to pull an x out here, x ln of x minus 1 plus c1, and I'm naming it a different name from the c because technically we did actually change that constant, so it is a different arbitrary constant. It's worth noting though. Okay, so just to tie this back in, the integral of ln of square root of x dx is equal to this, and that's equal to this, which we found. Okay. Integration by parts, super useful. Definitely be comfortable with that. Okay, and the last thing I wanted to run through was just a quick example of a trigonometric integral. So let's say we have sine cubed of x cosine squared of x dx. Now recall that we have cosine squared of x plus sine squared of x is equal to 1, okay? So there are generally a few ways to approach these because we have these identities and they're very useful. Some of these approaches will lead to a dead end though, okay? So first approach, let's say, okay, well, we have this nice cosine squared here, right? That seems like it's kind of begging us to use this Pythagorean identity here. So if we do that, Then we have the integral of, okay, we have sine cubed of x times 1 minus sine squared of x dx, which, okay, we've gotten everything in terms of sine now, right? But at the end of the day, we're trying to integrate, well, we have sine cubed of x minus sine to the fifth of x dx, and we don't really have a rule for integrating these things. So let's scrap that. Let's try the other way. So generally, one of the approaches is you, I say pull off, but it's kind of what you do is you factor. So let's say we take out a factor of sine. We have sine squared of x, cosine squared of x, dx, right? And let's try to apply our Pythagorean identity here instead. Let's see what happens, okay? So we have sine of x times 1 minus cosine squared of x times cosine squared of x dx. And I'll go ahead and distribute this through. So this is sine of x times cosine squared of x minus cosine to the fourth of x dx. Okay. And then we can distribute and apply the linearity of the integral to split it. Okay. So I'm just going to erase a little bit here. So we have the integral sine of x cosine squared of x dx minus integral sine of x cosine to the fourth of x dx. Okay, but both of these are just u sub problems now. Now we just say, okay, well, what if u is cosine of x? Then du is minus sine of x dx. And it's because we had that extra factor of sine in both of these that's gonna allow us to go ahead and solve these integrals. So just as a little Calc 1 exercise refresher, just kind of wrap up the u sub on this one. It shouldn't be anything too far out of reach for anyone, but it's I think I covered a little bit of everything I wanted to cover. Again, you know, don't be afraid to ask me questions. I'm going to wish you all good luck on the celebration of knowledge, and I think I'm going to wrap it up here. Thank you.